Now, as wireless technology becomes a critical part of safety and mission-critical systems like autonomous driving, we need new test techniques in which the instrument must be able to emulate the world around us in real time. To tell us about the exciting application of automotive radar test, please help me play a video by Niels Koch, the Director of Radar Research at Audi.
The average person is spending 3 years behind the steering wheel. There is a tremendous need to make this time more productive and safer with innovations like autonomous driving. Radar is the key technology of the future. It makes navigation possible and ensures that it can be done reliably and safely. At Audi, we spend a lot of time testing critical systems like radar that they will not fail in the field. This requires advanced approaches to testing. For example, using hardware-in-the-loop simulation, we emulate 10 years of sensor environment within a few weeks. We turn to NI Platinum Alliance partner Konrad Technology to help us to develop a target emulator based on LabVIEW and PXI. With the PXI vector signal transceiver, the combination of the industry-wide bandwidth and the low latency software allowed us to discover an automotive radar sensor as never before. With target emulation in the lab, we could identify critical bugs in our radar module that could not be detected before.
So to help us show off Audi's target radar simulator, please help welcome the architects of that system from partner Konrad Technologies, Michael Konrad and Dominic Eyerly.
Hey. Hey, Charles.
Hey, welcome to the stage, Michael.
Thank you.
Yeah, thanks for being here. So there's a lot of new challenges with automotive radar tests. Tell us about the new challenges.
Yeah, first we have to realize that a radar system consists of a hardware transceiver and software. Testing the radar software is the most difficult part because it requires us to test the system over a large number of different scenarios. One of the reliability standards Audi must test for is called Automotive Safety Integrity Level D, or ASIL-D. This standard represents one of the industry's most stringent safety requirements to prevent serious injuries or life-threatening accidents. In order to validate a radar system that meets ASIL-D requirements, we have to prove that a car can drive more than 10 million kilometers without any fault. 10 million kilometers, the equivalent is driving around 250 times around the world. If I drive with 100 kilometers per hour, 24 hours a day, it would take me more than 10 years to drive that distance. To efficiently test a radar system, we have to replicate its environment in the lab using a target simulator. Our target simulator is based on National Instruments signal vector transceiver and LabVIEW, combined with up and down converters that operates in the 76 to 82 gigahertz radar band. We have recently upgraded our system to the second generation VST because its wider bandwidth allows us to generate an object's distance with better precision. Of course, the software inside of the VST's FPGA is a secret recipe. Software running on the FPGA uses signal processing such as Doppler shift and delays to generate radar signals bouncing off real-world objects.
Now, I know we've got a demo over here next to the beauty Audi vehicle. We have an automotive radar sensor on the tripod on the stage through a chamber to a vector signal transceiver mounted behind.
Yeah, so first we will run a common scenario it called star pattern. In the LabVIEW VI, the target simulator will emulate the RF response of the target, moving according to this pattern. On the right side of the screen, you can observe the software GUI of our radar sensor. The white dot in this GUI represents the location of the detected object. When Dominic runs the demo, we can see that the white dot is moving according to the star pattern, just like in the simulation. The flexibility of the software allows us to generate any kind of pattern. As we were speaking, Dominic has loaded the lane change scenario and we are already testing the sensor.
Right, now just to reiterate, that white dot you see on the right side of the screen is the output of the radar sensor. It's what the radar sensor is seeing. Just like the aerospace example we saw earlier, the VST is effectively tricking the sensor into believing it's seeing objects in the real world. The ability to run LabVIEW software inside the vector signal transceiver FPGA gives us the ability to simulate any scenario in real time with extremely low latency, a capability that makes the second-generation vector signal transceiver the instrument of choice for demanding applications like automotive radar test. So what's next for your system?
Oh yeah, a lot of stuff. So with regulatory requirements still evolving, we continue to adapt our test system to future radar scenarios, both in design and manufacturing floor. The dream of fully autonomous driving requires technologies that expands beyond radar. Future vehicles will better utilize sensor fusion, combining signals from GNSS, radar, camera, and even LiDAR to better navigate. LabVIEW in Peak's Eye is the ultimate solution to test for sensor fusion. With its synchronization capabilities, instruments from DC to RF, bus interfaces like CAN, we expect to tune our system to simulate even much more advanced sensor technologies in the future.
Michael, thank you very much. Amazing demonstration.
Thank you.
You know, the pace of change in wireless technologies is exciting and breathtaking, but it's putting enormous time to market and cost pressures on our customers as they try to bring us devices with more bandwidth to help us instrument our world and help keep us safe. With the release of the second-generation vector signal transceiver, National Instruments is ready to help our customers solve the challenges of tomorrow, today. Thank you very much.